Hello, everyone. My name is Ian Botsford. I'm here to talk to you today about turbocharged Kotlin native on AWS Lambda. So this whole talk was born out of an experiment that I did a few months ago where I wanted to see if I could create a runtime framework for AWS Lambda that was built on Kotlin native, that could use strongly typed handler methods, where we could bring our own types and then deploy to Lambda so that we could then measure the performance and optimize and iterate on it to try to get the best performance possible. This is an example of what I wanted the handler function to look like, and you can see my cool request and my cool response are in here as the types that I'm bringing to this handler that the framework should ideally not have to know anything about. It should just handle sort of transparently. So a quick refresher on AWS Lambda for those who are semi-familiar or not yet familiar. It's a function as a service. You upload your code into the cloud. AWS executes it for you. There's no compute infrastructure for you to manage. It's kind of hands-off. It's just the code and the service that runs it in the cloud. One of the reasons that I really like Lambda is that it's highly scalable. It will reuse existing instances of a Lambda handler if that handler's idle, and it will launch new instances when all the existing handlers are busy. Unfortunately, launching new instances brings about an effect called cold start latency, where starting a new instance takes a little bit of time because the Lambda service has to provision a new instance somewhere. It has to load your code onto that instance and begin executing it. And then that code has to begin a polling loop where it continually asks Lambda, are there any new invocations for me to respond to? Out of the box, AWS supports a handful of runtimes that are customized for individual languages, including Java, Node.js, and a few others. But I was interested in going with my own custom runtime because none of these would work directly for Kotlin native, and I really wanted to see what the performance of Kotlin native would be on Lambda. So down at the bottom of this list, there's a mysteriously named OS-only runtime, and it turns out that's the key to writing your own custom runtimes for Lambda. So what does a custom runtime consist of? Well, like I mentioned, it's based on the OS-only runtime, which gets you a distribution of Amazon Linux 2 or 2023, depending on what you choose. You are responsible for creating an executable that forms the bootstrap or the entry point for the Lambda. You're also responsible for communicating with the Lambda runtime client, which is how you receive information about invocations that the handler needs to respond to. You do that by executing a polling loop where you ask Lambda, are there any messages? You hold the connection open for a certain amount of time. If it responds, great. You do your business logic and you return a result. If it doesn't, then you time out that poll and you start another one. And when you get an invocation event, you evoke the handler that you need to complete your business logic. This diagram shows a little bit about what the process looks like. Requests come into Lambda as a JSON blob. The Lambda service interprets it and it dispatches it to whatever Lambda instance it needs to, either an existing one that's already warmed up and executing, or a new one that needs to be provisioned. And inside that Lambda instance is the Lambda runtime running as a local web service. So communicating between the bootstrap and this Lambda runtime are relatively fast, but it does happen over HTTP, and that will become critical in a later part of the slides. At the bottom of the diagram there is the bootstrap executable. This is the thing that we need to provide for Lambda to be able to execute our handler, and the thing that I need my project to generate. And then inside of that bootstrap executable is the core business logic. It's the handler itself. So everything that's not polling the Lambda runtime, serializing and deserializing events, communicating over HTTP, that's what goes in that handler block. All right, so I started putting together a basic project where I figured I would need a few different modules. One, I would need a kind of Gradle plugin for users to apply to their own Gradle project and that they could use to identify the handler that they wanted to use in their own code, and any sort of configuration options for Lambda. Next, I would need a Bootstrap module. This would be the thing that would actually generate that pink box on the previous diagram, that overall executable that runs the polling loop and invokes the handler. And then finally, I need something for that HTTP connection. I need some sort of HTTP library that can communicate back and forth with the Lambda runtime. And I decided to go with two of the most popular options here for HTTP, that is curl and then OpenSSL for handling TLS. And because it's Kotlin native, I will be invoking them via C-interop. So this is kind of a layout of the project. You can see that the user code ideally only depends on that Gradle plugin or only uses that Gradle plugin. The Bootstrap has a dependency on Kotlin X serialization for handling the JSON conversion to our business types. And then libcurl depends on the curl and the OpenSSL libraries. All right, so let's dig into that libcurl module a little bit and talk about the C compilation and how that's going to work with our Kotlin native executable. So I decided that the best way to, well, I decided my initial attempt to do this would be to include curl and OpenSSL as submodules of my own Git repository that I was forming. This would be so that I could then build those libraries as part of my overall project build by creating Gradle tasks that invoke the configure scripts and the CMake builds for each of these libraries. If you're not familiar, those are common ways that C libraries are compiled or configured and compiled. So I just decided to wrap them in a simple Gradle task like you see down here at the bottom. There's a few things omitted from there, like you can see with that, etc. But basically, I just need to invoke two commands, or three commands rather, the configure script, the make command, and then the make install command to move my binary to where I need it to be. A few other notes here was that because I'm compiling the C code myself, I'm not using precompiled binaries. I want to make sure that the tool chain that I use to compile them matches the tool chain that Kotlin native will use to compile my Kotlin code. So I use the Conan tool chain, its C compiler, its linker, so on and so forth, so that there would be less chances of binary incompatibilities or surprises along the way. And then also I decided to use static linking because just generally static linking is faster than dynamic linking at runtime because there's not a lot of dynamic loading of modules or searching of paths to find your dependencies. They're all just built into one binary. And then it also simplifies integration with the OS level libraries. I don't have to worry about dynamically finding the pieces of code that I need from the OS. I can just rely on them all being in that binary itself. Next up, now that I've got my C libraries compiled to basically C executables that Linux could run, now I need to wrap them so that Kotlin native can invoke them. So I create a C-interop definition file, which just kind of points to where my headers are, to if there's anything I want to filter out, and to any additional linker options that I need. Fortunately, I didn't need that many, and it was pretty easy to get this definition file set up, and then also to write the Kotlin target that then depends on the C-interop, and the C-interop depends on building curl itself. What I didn't show here on these slides for brevity is that the curl build depends on the OpenSSL build, so you can see that there's a bit of a chain of dependencies here, but basically the core part of the magic here is making sure that your Kotlin compilation depends on the C compilation happening first. A few other features of this module before we move on. As I mentioned, HTTP is the method by which you communicate with the Lambda runtime, so I needed to create an HTTP client interface, and I decided to keep it as simple and as abstract as possible because curl, actually, I came to learn, offers two different flavors of HTTP client under the hood. There's the curl multi, which is a multi-threaded sort of high concurrency client. And then there's curl easy, where it's meant to be used in a single-threaded manner, and you're responsible for handling concurrency in your own application. So with my initial attempt, I thought, well, it's a no-brainer. I would want to use the multi-threaded version of this because I'm probably going to be doing some multi-threaded work. And then the other component here in the libcurl library is some sort of minimal client that wraps that HTTP engine and handles things like the infinite polling loop. So here you can see there's a loop method that accepts a serializer and deserializer. It takes a reference to the handler that the user will pass us later. There's a Lambda environment which contains some interesting stuff, and then a thing about exception handling. But the interesting thing is that this loop method has a return type of nothing, which means that we don't expect it to ever stop executing. Lambda is set up in this way where it will invoke a bootstrap, and it will expect that bootstrap executable to keep executing. And if it ever stops, then Lambda thinks that the instance has gone bad, and it will recycle it. So we keep our instance polling forever, and when Lambda decides the instance is no longer needed, it will forcibly shut it down for us. The other thing that's in this interface is just some basic error handling to let Lambda know if anything went wrong during the initialization, and if we know that the instance is unhealthy, we can take it out of commission before it starts receiving traffic. Okay, and then since this talk is about turbocharging Kotlin native and getting the most performance, I thought it would be helpful to identify a particular performance metric here to optimize on, rather than trying to optimize everything all at once. So for the purposes of my experiment, I went after cold start latency specifically. The runtime latency of Lambdas is also very interesting to optimize, and over time, it probably contributes more to your overall latency. But cold start is one of those really tricky problems that people have invented a lot of solutions to try to get around. And so, in particular, some of the existing Lambda runtimes, like the Java runtime or the Python runtime, have very large cold start latencies. So if I'm going to show to myself and to the rest of the world that Kotlin native truly belongs on Lambda, I think I want to start by optimizing the cold start latency. So the procedure for doing that is going to be to write a pretty trivial function for the Lambda to execute, to invoke that function using an additional argument that's not the default, where we say the log type is tail, which means that when we execute this function and when it finishes, we'll get back the end of the logs for the execution of the function. The cold start latency will be reported in those logs, and so we can use that to see what our results are. But the problem is that every time we execute a Lambda function, Lambda will look first to see if there's an existing instance out there that's idle. And if there is, it's not going to need to provision a new one, and therefore there will be no cold start. Now, normally this is exactly what you want, because you want your existing instances to be reused and you don't want to pay that cold start penalty. But if I'm measuring cold start penalty, then I want to force it to be a fresh instance every time. So the way that you do that is by updating the function in some way. You can upload your code again, you can rename it, you can create just n number of copies of it. But the simplest method that I found was to, I didn't note it on the slide apparently, was to assign an environment variable to that function and then just change the value of that environment variable in the configuration. So that's a quick and easy way to kind of iterate the function and make it appear new every time you execute it. So then I wrote up a quick script to do all this for me, and then to measure, I picked 100 samples arbitrarily. That seemed to be a good window beyond which the outliers stopped affecting the overall latency benchmark. And then here's an example of what the CloudWatch logs look like coming back. The important bit is down there at the very bottom, highlighted in blue, that init duration. That is our cold start latency. So for this fictitious example right here, the init duration was just under 79 milliseconds. That's our cold start latency, and that's what we're trying to get as low as possible. Okay, so I did a bunch of initial setup. I didn't try to optimize anything from the start, aside from choosing sensible defaults that I thought would work well, like static linking and the curl multi-threaded engine, so on and so forth. So this is before any of my intentional optimizations. I ran my benchmark script. I saw some interesting ranges here for min and max, and a standard deviation that was within 5 milliseconds. But the key metric here from my benchmark script is the median latency. This is the point at which 50% of calls will be under this latency and 50% of calls will be over this latency. So it's a good kind of metric that's a little bit more stable than a straight average would be. So next up, I took this number, the 78.59 milliseconds, and I compared it to the existing AWS Lambda runtimes that are out there. And I was pretty surprised to see that just out of the box, with no optimizations done, it was already faster than all of the existing AWS Lambda runtimes. It beat out Python by just a tiny bit, but the others, it's almost twice as fast, sometimes 3 times as fast. So that was pretty surprising, but I wasn't happy with that result. I wanted to keep driving it as low as I possibly could. So I asked myself, how can I do better? What kind of ideas can I think of here? And I came up with 5. Can we strip any more debug symbols out of the executable that's being generated? Get it as small and as compact as possible so that it's easy to transfer and easy to load into memory on the Lambda instance. Can I increase the amount of memory that Lambda uses to run this function? Documentation makes some insinuations about performance and memory that I'll get into later. Can I switch the architecture of the code and of the Lambda instance from the default of x86-64 to ARM64? Might be worth trying. I mentioned earlier that I took that curl multi HTTP client as my default engine. Maybe the easy engine is actually more performant. I don't know. Let's find out. And then lastly, can I do any optimizations of my C library dependencies of curl and OpenSSL? Can I tweak how they're compiled or what options they're compiled with to get them even more performant? So with that, I decided to work on my first idea, which was stripping debug symbols. The way to kind of analyze the libraries that are built is with a bin tools executable called readelf. This will basically give you an overview of all of the components or all of the sections of your executable and roughly how much space they occupy. That big text block, which is in blue, which occupies the majority, that's the code that's actually executing. That's your business logic, that's the polling loop, that's all executable code. The rest of these are various forms of data, of metadata that are useful sometimes in building or running or linking. But 2 of them leapt out at me, and those are the symtab and the stirtab sections. They stand for symbol table and string table. Basically, they describe the symbols within our executable, everything from what size they are and what location they should be loaded into in memory to what their names are. So then this includes, by the way, symbols that are inside your code and inside the code of your dependencies, things like main, printf, standard error, so on and so forth. They actually occupy quite a notable portion of the executable. And I realized after looking at them that they're not really used at runtime. They're not loaded into memory. They're not used by any executing code. They're only used by things that kind of happen alongside the runtime, like debuggers. We'll hook into those to give you friendly names when you're looking through your running code. Symbol inspectors like readelf itself or like the nm utility. And then lastly, they're used for stack traces. So I did realize that by stripping these out, that might mean that then if I had exceptions in the future, the stack traces would be pretty incomprehensible to any average reader. But nevertheless, I decided to give it a go. So I stripped them out using the strip command, which is also part of bin utils. It's part of most Linux distributions, and it's a relatively simple command to execute. And then I ran my benchmark script again and compared it to the original results. It did strip out quite a bit of code from my binary. So it went from a little under 11 megabytes to just under 9 megabytes, a savings of about 17%, which I thought was pretty good. But unfortunately, that did not translate to any performance improvements. My cold start times were roughly the same, in fact, well within a margin of error, so they're statistically insignificant. And therefore, there's not enough here to warrant the loss of stack traces and debuggability. So this idea I had to nix. Moving on, I had idea number 2 to increase the Lambda memory. This came about from documentation about Lambda memory and its relationship to CPU performance. First off, when you provision a Lambda function or configure a Lambda function, you specify how much memory will be allocated to it to run. And you can go from anywhere from 128 megabytes to 10 gigabytes. The performance scales proportionally with the amount of memory that you have, because the more memory that you allocate, the more virtual CPUs your function gets to execute on. There's a reference point in the documentation which says that if you allocate 1,769 megabytes, which is a very odd number, you will get exactly one virtual CPU assigned to your function. And so I did a little bit of testing and calculation and came up with this table that shows the default and the minimum amount you can allocate to a Lambda function gets a tiny sliver of a virtual CPU, less than 10%, whereas the 10 gigabyte maximum allocation gets you almost 6 virtual CPUs to execute on. So in theory, more memory, better performance, time to test it out. I ran my test, my benchmark script, with the default 128, and then I ran it with 512 and that reference point of 1769. And lo and behold, my cold start times are unaffected. They are still roughly the same, still within the margin of error. So curiously, this had no measurable effect on cold start. I went back and did some reading later, and it turns out that, as I mentioned earlier, those sections of the executable, the symbol table and the string table, are not used at runtime. They're not even loaded at runtime. So they don't contribute to the load cost of your executable, and apparently the 2 megabytes of data that we saved was not significant enough to cut down the distribution time. So in retrospect, it makes a little bit of sense why this didn't work out. But this was my second idea in a row that failed. I was getting pretty bummed here. I decided to keep going, but I was starting to think that this experiment wouldn't yield anything meaningful. Next idea was switching the architecture. So x86-64 is the default architecture if you don't customize anything, but when you're creating your function, you can choose what you want. And interestingly, the ARM64 architecture for Lambda functions uses a specific processor that AWS makes and supports, the Graviton2 processors. These have a larger L2 cache, a larger on-chip cache than most other processors that are available for Lambda functions or for general compute. And they also contain instruction sets that are highly optimized for running, cyclic redundancy checks, cryptography, even ML inference. That last one isn't particularly interesting to my experiment, but the first two are, because CRC and cryptography are used in HTTP communication back and forth to that Lambda runtime. So maybe that could get me faster performance. Who knows? Of course, the caveat here is that you can't always just switch your architecture from one to another. You need to make sure that you would have ARM-compatible, workload, dependencies, code that could run in that architecture. So this wouldn't be a general solution that necessarily everyone could use, but since I was starting from scratch, I figured, why not? Let's give it a shot. Okay, I ran my benchmark script again. I braced myself for the worst, that there would be no difference. But this time, I actually saw some success. My baseline, my x86-64 invocation took, like I said, just under 79 milliseconds. And the ARM64 execution took a little over 61 milliseconds, which is a savings of about 23%. So that seemed like a pretty significant win. And it led me to the conclusion that I should use ARM64 over x86-64 if possible. Again, the caveat is that I need code and dependencies and a workload that can execute in that architecture, but if I can have it, great. Okay, so feeling bolstered by my one success after 2 failures, I moved on to using curl multi, or switching from curl multi to curl easy. Curl supports the 2 engine types that I mentioned earlier, and here's some of the differences between them. The Curl Easy client has a simpler interface. It's meant to be synchronous and blocking, meaning that there's only one transfer happening at a time per thread. Your application is responsible for flow control. I realized that the flow control bullets are swapped. They're in the wrong places. So in Curl Easy mode, your application is responsible for handling flow control, for handling concurrency. In Curl Multi, it's the other way around. And then lastly, the Curl Easy engine has connection pooling that is per thread, basically per easy handle, which there's one easy handle per thread. Curl Multi, on the other hand, it's much more complex. It's built on top of Curl Easy, and it actually dispatches to Curl Easy for most of its work. It's asynchronous and non-blocking, which means that there are multiple simultaneous transfers happening within a single thread. The library itself handles all of the flow control. Again, those columns are switched. But then the connection pooling that you get is shared across all of the threads that you have. You don't have to handle connection pooling sharing yourself. So I wondered, could using the simpler HTTP client give us better performance? So I loaded up my benchmark script. I ran it again using my previous 61 milliseconds as a baseline. And I found that using curl easy actually does reduce the cold start time by a significant amount, about 20%. So this seemed like a pretty big win, but it comes with some caveats, because curl easy, again, is meant for simple workflows without threading. And if you want threading, you're going to have to handle more of that yourself. So the caveat here is you would need to stick with curl multi if you had a highly complex or highly concurrent workload. The intent of this Lambda runtime was to not just use curl to communicate with the Lambda runtime itself, but to also give it to the handler for whatever the handler needs for HTTP. Presumably, your Lambda function may reach out to other functions, it may reach out to other AWS services, and giving it a pre-configured, pre-warmed HTTP client was part of the job. So this could affect how the handler runs and what the handler is capable of, but for very simple Lambda functions, ideally the kind you want to start super fast, curl easy seems like a win. Okay, we move on to my last idea, optimizing the curl and OpenSSL builds. This one was the one that took me the longest because there was a lot to investigate. C libraries typically have a bunch of configuration options and build options that you can customize. For OpenSSL, a couple of them leapt out at me. There's actually a list of what feels like 100 options you can configure for OpenSSL, but I highlighted these 4 because they seemed the most interesting and like the quickest wins. I could enable no deprecated, which would turn off the building and the publishing of deprecated APIs from previous versions. Because my client, my HTTP client, is going to be built from relatively recent source code, I don't think it needs to rely on old deprecated APIs. So I can skip those as part of the build. I can also remove support for particular ciphers that are not used in SSL. So the DES cipher is unused in modern TLS. I don't need that. I can pull it out. There was a legacy crypto provider in OpenSSL that offered a way to kind of switch between crypto algorithms. Didn't need that. There was also built-in support for the QUIC protocol, which is a UDP variant of HTTP. I knew I wasn't going to need that for any of my calls, so I customized all of that to remove a bunch of code from the OpenSSL build and to get the OpenSSL library to be smaller and more compact. On the curl side of things, there is, again, hundreds of different options for you to customize about the build. I picked out the 5 here that seemed interesting to me. Disabling AWS SIG-v4 support. I don't need my HTTP engine to sign any requests to AWS. I also don't need Kerberos authentication. That's not any sort of modern authentication that my web service or my cloud function is going to use. There was an option to drop unused code and data from the final binary, and I was surprised this wasn't turned on by default, but I figured that sounds like something I'd want to do. Turning off support for SSH2, and then also turning off the usage of old deprecated OpenSSL APIs seemed like a good idea. If OpenSSL isn't built with those deprecated APIs, then curl doesn't need to call them, doesn't even need to know they exist. Okay, so I ran one last benchmarking script, compared the results, and this time the savings were a little bit more modest. I started at 49 milliseconds, I got down to just under 46 milliseconds, a savings of about 7%. I did save a little under 2 megabytes of code, though, which seemed like a good savings. So that's a win for binary size, but a modest win for latency. So this seemed like a win overall. Optimizing my C libraries, build and configuration dependencies got me some performance improvements, but there are some caveats here. Customizing these options is kind of an advanced feature. These options have defaults for a reason. It's because they're the best and most supported for the general use cases by the authors of these libraries. And so tweaking them, especially when there are multiple C libraries that need to communicate, may introduce some incompatibilities at build time, or even worse, at runtime. As an example of this, those no deprecated options that I was talking about earlier, they actually had slightly different interpretations in curl and OpenSSL. So curl's idea of no deprecated functions in OpenSSL actually included an additional reference to a C macro that was removed when I turned on OpenSSL's no deprecated build option. So my curl library wouldn't compile anymore because it was looking for some macro that was no longer defined. I had to work around that by manually adding some additional CMake logic to define that constant. And fortunately, that was the only incompatibility I discovered, but the potential is always there for there to be more, the more of these options that you start to tweak. So my recommendation is to always read the docs very carefully, to always test these optimizations very thoroughly to make sure that they don't fail at build time and they definitely don't fail at runtime in surprising ways. Lastly, I thought it would be interesting to come up with some additional ideas, ways that I could further work on this if I had more time, which I didn't, unfortunately. I could disable more OpenSSL and curl features, disable and or customize more of these features. I could also look at replacing OpenSSL altogether. There's lots of different SSL libraries or implementations out there. Maybe one of them would be faster for my particular use. Similarly, I could replace curl. Maybe Neon or Apache Surf would be a better option. Curl's pretty widely used and pretty heavily optimized, so I'm not sure if that would work out, but it's always worth checking. I could remove Kotlin X serialization from the picture. Now this would kind of break one of the premises of my experiment that I wanted, which was automatic serialization and deserialization, being able to use my own strongly typed handler function. But if I really wanted to squeeze the most performance out of this that I could, then maybe that's an option worth pursuing. I could skip using coroutines. When I wrapped the HTTP engine and when I built the handler, they were built using suspend APIs. But coroutines have some overhead and maybe some manual threading or complete lack of threading, or concurrency rather, would make this faster. And then lastly, I could attach a profiler to my executable. I could take snapshots of it executing. I could see where the hotspots are, where it's spending its time during execution, and use that to sort of guide my optimization to specific target points. So, like I said, I wasn't able to test any of these ideas, but if I get more time in the future, these will be things that I'll be looking into to see if I can get that time down even further. So, in summary, here's what I found. These are the optimizations that seem to make a difference. I started with a baseline time of about 79 milliseconds. I got it down to about 46. And the architecture, the HTTP engine, and the C library configurations were the things that made those differences. So I'd like to be able to show more lines of this table in a future version of this talk by using some of those other ideas. Who knows? Some other tips to use while you're thinking about optimizing Kotlin native, not just on Lambda, but in any environment, would be to compile your native libraries with this Conan toolchain, especially if you're going to integrate the C library compilation into your Gradle project. Making sure that they're all compiled with a unified toolchain is the way to kind of remove a lot of potentials for binary incompatibilities or gotchas. I do recommend you stick with curl multi for complex or highly concurrent workflows, or whatever version of an HTTP engine that you use, whatever its multi-threaded variant is. That's probably the right thing for complex workflows, but for simple workflows, a simpler engine might work fine. Again, when changing your build and config options, make sure to read the docs and test thoroughly, because they will bite you if you're not very careful. And then lastly, keep exploring other ideas. Keep thinking of ways that you could attack the problem of latency and identify where it is and minimize it as much as possible. A bunch of the sample code that I showed here, and actually a full working implementation of a Kotlin native Lambda runtime, is available on GitHub. I've got the link here. I've also got a little QR code to scan that's off the slide. Well, the next slide has it. There we go. That's the QR code to use, which will also be available when the talk is posted later. But yeah, that is my talk. Thank you all for listening. I'll take any questions if you guys have them. If there are any questions, there's a roving mic, and then there's a mic over here in the center.
So besides the optimization, did you also consider the costs for the analysis, or just the performance? Because if it's faster, the costs will be also lower, right?
Oh, sorry, did I consider the
AWS
cost of
cost.
execution, the financial cost of
Yes,
execution?
yes.
No, I didn't, but you're right. Like the less cold start latency you have, the less overall latency you have, the less you are charged for each execution. I didn't measure that or take that into account much, but I would expect it to be a pretty proportional savings. So if I saved roughly 40% of my overall cold start time, I would expect that I saved roughly 40% of my AWS bill. But no, I wanted to optimize for just one particular measurement to keep the experiment kind of simple.
Okay, thank you.
Yeah. One up here in the front.
So, did you consider any of the like Ktor or Kotlin XIO for the HTTP interaction?
No, I didn't actually. I kind of wanted to use this experiment as an opportunity to interact more with some C libraries. That would be a great one of those additional ideas to test to see if the Ktor application or the Ktor client is faster. I'm not too familiar with the native implementation of Ktor. I've used the JVM implementation several times, but yeah, that's an interesting idea. No one else? Yes.
So have you tried out how the performance on the JVM looks if you enable like a lot of the features that recent advances have brought, like ahead of time compilation, etc.?
Yeah, so not as part of this experiment, but there is some published benchmarks on it from other authors. In general, things like pre-compilation via graalvm or other methods is a way to reduce cold start time quite a bit, but the thing that seems to affect it more for JVM workloads especially is snap start. Snap start works by kind of starting up your function in an isolated instance before any customers request it, and then kind of pausing the JVM there and then distributing a memory image of that paused JVM to the rest of your instances. That reduces cold start time quite a bit, but you have to be careful about how you architect your code in that situation. It imposes some additional kind of restrictions. So there's some trade-offs there with JVM. It can be faster than the example I showed up here, but yeah, I was really interested in Kotlin native for this particular experiment. Okay. Well, thank you very much, everyone. You've been a great audience. Enjoy the Cody Awards.